Howdy! We round out our module on primary structure by looking at a more modern technology for looking at protein sequences. It's used for metabolomics, proteomics, it's used for lots of things, but with respect to primary structure, we can take advantage of mass spectrometry technology to actually help us with sequencing. And I'm going to tell you how that works. So, mass spectrometry separates the fragments of a polypeptide on the basis of their mass to charge ratio. Usually these fragments are generated by trypsin digestion. So that's one of your toolbox enzymes used to cleave your proteins after lysines and arginines. And these fragments will fly differently towards the detector based on their mass to charge ratio. And so they'll hit the detector at different times, and you will get peaks for each one of the products in a predictable way. There are a couple of different types of mass spec. At the time of the printing of your textbook, it was electron spray, ionization mass spec, and time of flight mass spec, or MALDI-TOF. Both of these work in generally the same way. The products of your endopeptidases, like trypsin, are separated and then identified. And this is a simplification of how ESI mass spec works. Your sample is in a solution in a glass capillary at atmospheric pressure. A strong voltage is applied, and then it's shoved through a low vacuum in a nitrogen tube. This ionizes your particles, and some of those ionized particles will be larger than others, and they will be flying towards the detector in a gas phase, and they'll hit the detector at different times based on their mass to charge ratio. That's what M over Z means. And they will have different numbers of charges that are predictable for each of the different peptide fragments. And this gives you what we call a spectrum. A spectrum is usually peaks that are in as a function of time. And the spectrum is diagnostic, or a fingerprint for each different type of protein. All the genomes that have been sequenced can be deduced for their protein sequences, and we know that trypsin will cleave after every lysine and arginine, so we know what those products should be. And so there are algorithms that are in the protein databases that will show you what the actual mass spec is predicted to be for each protein that's been digested with trypsin. And we call that fingerprinting. And here is an example of a fingerprint of a protein that will tell us which unknown protein we have based on the mass spec. Now, you and I can't read this. Some people who do a lot of mass spec can probably tell us what this means, but the algorithms available on proteomics sites can tell you, based on your output, exactly what protein polypeptide chain went into the mass spec. And all of this is automated on the mass spec machines themselves, and then you can just look up the data on any one of these protein and DNA sequencing databases, which have lots of other valuable tools as well. So this is really the state of the art, although it keeps changing every day, for analysis of protein and DNA sequencing. And this, my bike, which tells me when I'm done, has covered checkpoint 3, which you can see in the slide sets, and check your understanding, your basic understanding of each of these different concepts that we've covered in the primary structure module. See you next time.